Hello and welcome everybody to lecture 4.2 on feedback control. In this video we will look at the problem of how to bring a dynamical system, say a quadrotor for example, into a particular goal state by giving the right sequence of motion or action commands. For example, in the case of a quadrotor, we often want to move it to a desired goal location, say above a landing spot or to the landing spot. And for that we need to generate, of course, a suitable control signal. And this control signal essentially corresponds to the controls that you give with the remote control. So you can change the roll and the pitch or the height and the yaw angle, the heading. And you could not do this blindly. You need to know, of course, where the robot is at the moment, and then you can compare this current location that you will have to observe through sensors somehow with your goal location, and then based on the comparison of these two, you can generate a suitable control signal. So before we go into more technical details, I just want to give you a very intuitive example first on what this means and what feedback control, what the generic idea behind feedback control actually is. So imagine, for example, that you get a morning shower and you get out of the bed and jump into the shower, and then you want to switch it on and you want to have your water to have a comfortable temperature, say of 35 degrees. So you are in this case then the controller that selects the water temperature, and you just switch on the valve or the mixer of your shower, and that will make the water flow of the system. The shower is then called the system in control theory, or the plant. And then you stand below the shower, of course, and then you can sense the temperature of the water. And then figure out that it's actually not at the 35 degrees that you expected, but much below. And so you feedback, and this is the idea of feedback control, and you feedback this measurement to the controller to take an appropriate action. So in this case, you first compare the observed temperature to the desired temperature. You observe that there is a certain discrepancy of a few degrees, and so you would turn the valve hotter to hopefully make the water warmer. And if necessary, you do this closed loop cycle a few times until the water has reached the right temperature. So much to the generic idea. Now let's look at this in a more technical way. It's often drawn in a block diagram like this. On the left side, you can see the reference signal or the goal state that we try to achieve. This goal state or desired value is compared to the current state of our system. And then this difference, the so-called measured error, is then fed into a controller. And this controller can be arbitrarily complex, but for this video, we just look at a proportional, a P controller, as you'll see in a second. And this controller then generates a control output. This can be, for example, a one-dimensional variable that just specifies whether we should turn it hotter or colder, or to move the quadrotor forward or backward. But it can also have multiple dimensions, as you will see later. And then this control goes into our system, for example, into the shower or the pipe system. And this control then changes the internal state of the system, and so the output of the system is its internal state, which we can then observe with one or more sensors to obtain a measured state. And this measured state is then fed back again or compared again to the reference value, and leads to an updated measured error that is used again by the controller to adjust the controls. So, as I said, the controller can be arbitrarily complex, but a very simple and very efficient controller that's actually used a lot in practice is just a linear controller that takes the error that we're getting in and multiplies it by a constant, the so-called gain. So this k here can be anything, any positive value in principle, In this way, we take directly the error values and to generate, the controls depend linearly on the errors. And then our system can, of course, also behave arbitrarily complex, but in the case of the shower example, and also for the quadrotor for position control, we can just treat it as a linear system. So we have the new state can be computed from the old state plus the control that we've given. So if we increase the temperature by 5 degrees, then we would just add +5 to the previous state of the shower, of the system. And there might be some error constant epsilon here that describes the system noise, things that are out of our control, like for example a changing temperature or water pressure in the water system. And then this system state gets observed by our sensor. Again, the sensor can be arbitrarily complex, but for the shower we could just assume that we have a linear temperature sensor that observes exactly the temperature from the system, plus some noise delta that changes in every time constant, but is distributed according to some distribution. Good. So now let's have a look what this does for our shower example. In the first plot, so now we assume we have this control law where the control output just depends linearly on our error. Now imagine that we start at, say, 25 degrees and we want to achieve 35 degrees in the shower to have it comfortably warm. Then in the first time step, the algorithm would compare this, the observed temperature 25 to the desired value 35 and find that there is a difference of +10. So it would feed back a control or it would generate a control of +10, and then within one time step this control would then change the temperature of the shower, and in the next time step we already have reached the 35 degrees, and because we are at the desired value already, the error term will become 0, and as a result also the control will become 0 then. Of course, this is not very realistic because you always have some noise in such a system, both in the process itself, so in the system, but also in the measurements or in your sensor. And now for this plot I added some noise in the measurements. So instead of returning exactly the right temperature of the internal state of the system, we get a noisy observation of that. But still we can compare this noisy observation with our desired value, and then with the same law as before, we can use that to generate a control. And as you can see, we again reach roughly the desired temperature, but you can also see that it is quite jumpy. For example, at roughly at 8 seconds time or so, we reach a temperature of 37 or almost 38 degrees, and then later at maybe 12 seconds time, it even drops down to 35. So this is probably not very comfortable in the morning to have such a temperature profile of your shower. Another problem here is that the controller always generates some control commands. So you can see that the green line here in the bottom plot is not reaching 0. It always changes a lot between plus and minus 4 maybe, and that this means that if you would be under the shower, you would have to constantly adapt the temperature, and that's of course not very comfortable, but also for a quadrotor this would be not very energy efficient if you have to give constantly controls just to keep the same temperature. So as you can see, if we keep it as before, if we choose k = 1, so directly use the error as the control, then we get a relatively poor performance. And now the question, of course, is how can we improve on that? And one very simple way is to lower this k, this gain, to a lower value, say 0.15, for example. That means that if we observe 10 degrees difference between our current value and the desired one, then we will only adjust it by 1.5 degrees, or try to adjust it by 1.5 degrees per time step. And that makes us somewhat more robust against noise. We kind of filter away the noise partially. but it also means that it takes much longer then to reach our desired temperature. So in this example, for example, the red line, which is the true temperature of the shower, reaches 35 degrees around 20 seconds time. But nevertheless, we can see that it keeps then the desired temperature relatively well, despite this large sensor noise that we have in our system. But the problem obviously is that if you lower the gain too much, then your system or your controller will get slower and slower, and it will take more and more time to converge or to reach the desired value. So you could think of how large can you make this gain that it still works, and you might also be tempted to make the gain larger than 1. And it should be noted that this is always problematic actually. For example, consider this example where we chose a coefficient of 2.15, and now what happens is that it always overshoots a lot because it finds that there is a 10-degree difference between the current value and the desired value, so it will multiply that by 2.15 and then add 20 degrees to that, and then be much too high, and then in the next time step it will find that it's that the temperature is way too high, and then reduce it and so on, and this will start to oscillate and actually increase, and these oscillations will increase over time. So be careful with too large gains. Another thing that happens often in practice, actually, when you program a controller, is that you might end up with the wrong sign, either in the coefficient or in the way how you compute the errors. So if you observe, when you're doing the exercise for this week, and you observe that your quadruler shoots away in one direction, then maybe check the sign of your error function or of your coefficient. So let's see what happens if we choose a negative coefficient. And then what we can see is that if the algorithm or our controller finds that the temperature is too low, it will even make it even lower then, and so the shower reduces the temperature more and more. This is a fun example, of course. The temperature drops to negative degrees, and then at some point converges to minus 272. So this is the absolute 0 point. And this is actually an interesting aspect that in most practical cases you can get saturation effects either in the state space, so that the shower cannot get colder than maybe 0 degrees Celsius, and that it can't get hotter than maybe 100 degrees, or you don't want to get it hotter than 60 degrees, so you have saturation in the state space. But at the same time, you can also have saturation in your control space, which means that you can't arbitrarily fast open the valve for hot water, for example, or you can't fly or accelerate arbitrarily fast with a quadrotor. And this is then called a control saturation, which just means that your control has a maximum and a minimum value that you can give. So for example, if you have to open a valve by hand, then maybe you can only rotate it at a certain speed. And this might mean that it takes a few seconds until you have opened it enough to get your 35 degrees of desired temperature. Time delays are another very important problem that you have in most practical systems, especially in a shower that you don't know, of which you don't know the dynamics. This can be a very tricky problem. So the thing is that you switch on, or you increase you try to increase the temperature, but nothing happens. So for example, here in time step 8, the valve is opened, or the temperature is being changed, but in the blue line, which gives us the observations from our system, nothing changes for 5 seconds because we have a time delay of 5 seconds, and only after these 5 seconds we get the first readings of the changed temperature. But by the time that we think that we have reached the 35 degrees, which is roughly at time step 19 here, the shower is already much hotter, like maybe at 38 or so, but because we don't know, we overshoot, and so it can take a while, or then we need to reduce the temperature again, give negative controls, to bring the temperature down to 35 degrees. And this first effect here is called overshooting. So if you're going beyond the desired value that you're actually trying to achieve, and if it goes back and forth around your desired value, then this is called an oscillation. And in the worst case, depending on how your delays are and what the dynamics are of your system, this can even lead to destabilization. One solution, as always, is obviously to lower the gains of your controller, but as we've seen before, this is probably a bad idea. It can help, but the disadvantage is that then the convergence takes much longer, and maybe you have to wait a few minutes then in the shower until you get the right temperature that you desire. So let's look at this time delay problem in a little bit more detail, because we will also need it for the quad rotors. The problem in general is that you might have several places where time delays can occur. Actually, in all of these components you could have time delays. So of course the most obvious one in the shower example is that the water pipe might introduce a time delay, a considerable time delay, if you have huge pipes with little water going through them. But also your measurement system, your sensor might introduce a certain delay, and also your controller or the communication between these components might introduce delays. And so one question here now is whether or not we can actually distinguish between the individual time delays from within the controller. And the quick answer here is that it's not possible to distinguish that for the controller. The dead time or the delay of the system or of the whole loop is not observable. It always appears as if you had a system with 1.2 seconds delay in this case. Good. So there is a solution for a simple solution to accommodate for delays, and that's the so-called Smith predictor, which allows you to use higher gains than you could use if you just ignore the delays. However, the Smith predictor requires a very accurate system model, and you might not have always such an accurate model. So the idea of the Smith predictor is as follows. Again, we have a controller that compares the current state or the current predicted state with the desired state, and then generates a control signal that we feed into the system that has a certain delay. But instead of using the output of the system or sensing the output of the system, we have a delay-free system model that we calibrated and that we think is accurate, or as accurate as possible, to model our real system. And this model is delay-free, so it gives us immediately the expected observation from the system at the current time step, and we can then feed that back into the controller to compare it to the desired value. Now, this by itself would only work if you have a perfectly accurate model, which of course is never the case in any real situation. And this is now where the Smith predictor idea comes in. We still have a sensor then that observes the system state, but remember, this observation set t is actually time delayed by a certain time delay. And what we now do is we also time delay our prediction set pred that we got from our system model, and we compare these two. And if our model is perfectly accurate, then the difference between the real sensor observation and the delayed sensor observation should be 0. If it's, however, not perfect, then we will get here a residual that we can feed back into that we can use to correct our delay-free prediction. And in this way, we can take advantage of both the delay-free system model, but we can also deal with deviations from that. So if our system model doesn't do anything, or is partially wrong, then we still have this normal error term that just considers the difference of the sensor and the model. So let's first look at a very simple example where we assume that we have a perfect system model of our shower and we have a 5 seconds delay. And then the Smith predictor results in a perfect compensation because we know exactly what's going on inside the system, and we can perfectly compensate for the delay then. Of course, this is completely unrealistic in practice because you never have a good model or a super accurate model. There will always be some parts of the system that you can model that you can't model exactly. And the other problem is that you typically don't know exactly about the delay. In some systems you know, but if it's a communication delay, for example, that you get through wireless, then this delay or the bandwidth might change as you fly, and it's not always possible to know how long the signal was traveling. So so because you have these uncertainties, the question is whether you should better over or underestimate the time delay. So let's consider first that if we would overestimate the time delay, what the result would be. And then the effect is as follows. So our system, the Smith predictor predicts too far into the future, which means that it thinks that just by giving a certain control command that we've already reached our desired goal location, because in a very distant future we already might be at the desired state, or we might even overshoot. So it will greatly reduce the controls in the next time step because it thinks that we're already going too fast, and then it goes and then it would project that into the future and then realize that it's actually too slow, and so it would go back and forth and oscillate. And as you can see, this is clearly not optimal, and it also leads to large changes in the controls, which is not what we want because this costs a lot of energy. An alternative then is to underestimate the time delay, and that's actually what's often done in practice, because then you don't get this overshooting effect of your prediction. Although you still have a certain discrepancy between your model and the actual system because you're underestimating the time delay. But in this way, you can use your model to compensate for half or maybe 90% of your time delay, and you consider the rest as the noise or the thing that you try to not model and just use directly the sensor readings. This leads, of course, to a slightly slower convergence in the end, but it circumvents oscillations and makes you approach the goal state nicely. Good. So this concludes the video then for this session. We've looked at the control problem and the feedback control problem in particular. We've introduced proportional control, and we've briefly looked at delay compensation using the Smith predictor. And then in the next video, we will extend this to full PID control and then apply that to position control for quadrotors.